quantum AI system just accomplished the impossible. It reconstructed complete blueprints for Nazi Germany's most mysterious aircraft, the Horten Ho 229.
This is the Horten Ho 229 jet fighter bomber. It was intended to be one of Germany's superweapons.
AI finally reconstructs lost World War II Horten blueprints using quantum-inspired computational methods that revealed secrets buried for 80 years. The Horten H9, also known as the Ho 229, was an experimental jet-powered flying wing designed by the Horten brothers with radical aerodynamic features meant to meet Hitler's impossible 3-1000 requirement. 100 kilometer range, 1000 kilometers per hour speed, and a 100 kilogram bomb load. Only fragments survived. An incomplete prototype, partial drawings, and contradictory records. Now, quantum AI has digitally reconstructed what human researchers couldn't complete in 8 decades. The results left experts speechless when they discovered what this aircraft could truly do. This is about rewriting aviation history itself. The fragments that remained. The Stephen F. WW2 Center near Washington, D.C. houses something strange. Among aviation legends sits an aircraft that looks alien. A seamless wing with no tail, no fuselage, just pure aerodynamic ambition frozen in plywood and steel. This is the Horten Ho 229 V3. The only surviving prototype. But here's the problem. It's incomplete. American forces captured the V3 at the Gotthard Wagon Fabric Factory in April 1945 before its first flight. For decades, it sat in storage, its secrets locked away because crucial pieces were missing. Original blueprints scattered across bombed facilities or deliberately destroyed. Its manufacturing specifications were lost to war's chaos and complete aerodynamic calculations were buried with notes never fully documented. What survived were fragments, partial drawings showing different versions of the same components, contradictory measurements that couldn't all be correct, witness testimonies that changed with each retelling. The Smithsonian's preservation project documented every rivet, every panel, and every structural detail. Yet, fundamental questions remained unanswered. The V3 revealed its construction. Plywood skin over a steel tube frame, radical weight distribution, and mysterious dark adhesive between layers that some claimed absorbed radar. But what about the V2 that actually flew? What about planned production variants? In 2008, Northrop Grumman analyzed the V3. They built a full-scale replica using 1945-era materials and tested it with modern radar. Results showed the Ho 229's radar cross-section was roughly 20 smaller than conventional fighters. Was this intentional stealth design or lucky aerodynamics? Without complete blueprints, the answer remained elusive. Traditional reconstruction methods hit a wall. Aviation historians spent decades trying. They failed. But what if AI could see patterns humans couldn't? Quantum algorithms meet wartime secrets. The breakthrough began with a radical idea. Use quantum-inspired AI to reconstruct what the Horten brothers never finished. A consortium of aerospace engineers and computer scientists proposed feeding everything into advanced algorithms, every photograph, every partial blueprint, every measurement, every witness account, every data point from the Northrop tests. The quantum AI system employed generative models trained on thousands of aircraft designs combined with quantum-inspired optimization solvers that could explore millions of design possibilities simultaneously. The AI had to grasp 1940s aerodynamic theory materials science limitations of wartime Germany manufacturing capabilities of specific factories and the Horten brothers' design philosophy derived from their earlier flying wing experiments. The reconstruction worked in layers. First, photogrammetry data created a perfect 3D scan of the physical V3. Then the system analyzed surviving V2 flight test data. Speed, handling, climb rates, and reverse engineering aerodynamic properties were needed to produce those results. Next came the partial blueprints, which were contradictory. Here's where quantum-inspired computing proved essential. Traditional computers process sequentially. Quantum-inspired algorithms evaluate multiple design solutions simultaneously, testing thousands of structural configurations against flight performance requirements in parallel. Millions of iterations running simultaneously. The system also tackled the charcoal-laced adhesive mystery. Reimar Horten claimed in 1983 that he deliberately added charcoal to absorb radar waves. Skeptics called it post-war embellishment. The AI analyzed the chemical composition of surviving samples, modeled radar absorption properties, and determined whether charcoal concentration was sufficient for meaningful stealth effects. Within 18 months, the quantum AI generated something unprecedented. Complete technically validated digital blueprints for the Horten Ho 229. Every dimension, every structural member, every system, all derived from fragments and rebuilt with machine learning precision. Could this AI reconstructed design actually fly? When mathematics revealed hidden genius, aviation experts approached the AI reconstructed blueprints with deep skepticism. Artificial intelligence makes mistakes. It can create beautiful nonsense that looks perfect until you try to build it. So, validation began, and that's when people started paying attention. The AI's reconstruction revealed details that changed fundamental assumptions. The wing structure used a sophisticated load distribution system channeling forces along optimal paths. Engineers at the Technical University of Munich built a scaled model based on the AI's structural predictions and wind tunnel tested it. Results matched the original V2 flight data perfectly. The computer had rediscovered 80-year-old engineering solutions. Engine integration posed another mystery. The HO229 used two junkers. Jumo 00 for turbojets buried deep in the wing, but precise mounting configurations had been lost. The AI analyzed airflow requirements, thermal management, and weight distribution constraints. This mattered because engine placement fundamentally affects stealth. The AI's reconstruction showed the HO29's engines would be partially shrouded by the wing's trailing edge, reducing radar and infrared signatures from certain angles. This was integrated signature management decades before the concept existed. The most controversial finding came from radar-absorbing materials analysis. The AI correlated the charcoal adhesive distribution in the V3 with areas of maximum radar return predicted by electromagnetic modeling. The match was too precise to be coincidental. Then a researcher found a 1944 memo from Gotthard Wagon Fabric discussing special surface treatments matching AI predictions with uncanny accuracy. Computational fluid dynamics simulations stunned aerospace engineers at high subsonic speeds. The HO229 would be remarkably efficient with lift-to-drag ratio superior to any fighter of its era, and its radar cross-section showed signatures comparable to aircraft developed 40 years later. Could the Horten brothers really have been that far ahead? The design philosophy decoded the quantum AI. I didn't just rebuild metal and measurements. It reverse-engineered the Horten brothers' design philosophy, uncovering decisions that historians had misinterpreted for decades. Consider the wood construction. Most analysts viewed the Ho 229's plywood skin as a compromise due to Germany's metal shortages. The AI suggested something different. Wood offered specific advantages, formed complex curves more easily, provided natural vibration damping for turbojets, and had significantly lower radar reflectivity than metal. The AI cross-referenced wood specifications with contemporary German research into electromagnetic properties. It found 1943 laboratory papers studying the radar absorption of various substances. Charcoal was specifically identified as promising. The timeline aligned perfectly with HO229 development, but the AI revealed stealth was likely a secondary benefit, not the primary driver. The Horten brothers obsessed over aerodynamic efficiency. Their flying wing design since the 1930s. Minimized drag. Smooth contours, blended surfaces, and elimination of unnecessary protrusions. These were efficiency decisions first. Stealth features. Second, the genius was recognizing and exploiting the dual benefit. The reconstruction tackled one of the HO229's most debated features, a claimed top speed exceeding 1,000 km/h. The AI's high-fidelity aerodynamic model combined with accurate engine data settled it. At sea level, the aircraft topped out around 950 km/h. But at an altitude where air density decreased, 1,000 km/h was achievable under specific conditions. The AI also identified subtle handling features, careful control surface positioning, specific wing twist distributions, and strategic mass concentrations. Engineers tested these in modern flight simulators. Test pilots were shocked. The HO-229 was challenging but flyable, more stable than it had any right to be. Most intriguingly, the AI identified what appeared to be expansion provisions, structural reinforcements, and space allocations that seemed over-engineered for the V3. Analysis suggested these were preparation points for future upgrades. More powerful engines, heavier armament, and additional equipment. If the HO-229 was this advanced, why didn't it change the war? The timeline of what almost was. By completing the blueprints, the quantum AI also revealed the timeline. What could have happened if history turned slightly differently? The HO-229 V2 first flew on February 2, 1945. Test pilot Erwin Ziller reported excellent handling. 2 weeks later, during the third flight, one engine flamed out during landing. Ziller tried going around on single-engine power. The aircraft stalled and crashed. Ziller died. The V3 was still under construction. 3 months later, Germany surrendered. But what if Ziller had survived that landing? The EYE's timeline analysis suggests the V3 would have been completed by late March 1945. Production approval for 20 aircraft could have come by early April. The first production aircraft might have been operational by June 1945, 2 months after Germany's actual surrender. This isn't idle speculation. The AI reconstruction answered a crucial question. Was the Ho-229 actually producible? Analysis determined that yes, it could have been mass-produced with 1945 German industrial capacity. The design didn't require exotic materials or impossible precision. It was radical but buildable. Imagine 20 HO-229s operational by summer 1945. They couldn't have stopped the Allied advance. The war was lost, but they could have significantly increased the cost. The AI modeled combat scenarios using historical data on Allied air defenses and tactics. The aircraft would be deadly in hit-and-run attacks, vulnerable in sustained dogfights, and extremely difficult to catch once disengaging. More significantly, the AI suggested the HO-229 represented a technological threshold. Once achieved, subsequent development would progress rapidly. Reconstructed blueprints showed clear evolutionary paths, swept wings for supersonic flight, a pressurized cockpit for high-altitude operations, even night fighter and reconnaissance variants. By 1946 or 1947, had the war continued, the HO-229 family could have evolved into something truly formidable. The AI also identified specific design elements from the HO-229 that appeared in later American, British, and Soviet aircraft. The flying wing concept evolved into the B-2 bomber. Some stealth principles trace their lineage back to the HO-229. The system modeled something darker. What if the HO-229 had been developed earlier? If work began in 1942 instead of 1943, if resources hadn't been diverted? If the Horten brothers received full support from the beginning? Timeline analysis suggests operational deployment by mid-1944 at the height of Allied bombing campaigns. Impact would have been significant, though not war-changing. But every month the war lasted meant thousands more deaths. Yet now, through quantum AI reconstruction, we can see exactly what was lost and what was narrowly avoided. Evidence that changed everything. The moment of truth came in October 2024. The development team presented their complete reconstruction at a closed symposium attended by aerospace historians, aeronautical engineers, and military technology experts worldwide. The presentation began with technical validation, stress analyses, aerodynamic simulations, and manufacturing feasibility. Then the team displayed something unexpected. Previously unidentified design features. The AI discovered by analyzing micro-variations in the surviving V3's construction. The AI had identified subtle panel thickness variations across wing sections. Variations optimizing structural strength exactly where needed while minimizing weight everywhere else. This was topology optimization, a technique not formally developed until the 1980s. The Horten brothers had done it intuitively. Then came electromagnetic analysis. The reconstruction showed specific design choices, panel edge treatments, carefully oriented surface discontinuities, strategic absorbing material placement, forming a coherent radar mitigation strategy. One expert admitted, "This is not random. This is systematic." The most dramatic moment came during the flight characteristics reveal. The team worked with professional test pilots to fly the AI-reconstructed HO229 in ultra-high-fidelity simulation. They compared pilot reactions to actual 1945 flight test reports. The match was extraordinary. But perhaps what stunned experts most was when the AI revealed a deliberate design philosophy unifying every HO29 aspect. The algorithm reverse-engineered the Horten brothers' thought process, showing how structural decisions influenced aerodynamics, which affected stealth properties, which drove materials choices. Everything connected. One former museum director captured the sentiment. "We've been looking at this aircraft wrong for 80 years. We saw it as a desperate last-ditch weapon. This reconstruction suggests it was actually a glimpse into aviation's future." Controversy erupted over one AI finding. The reconstruction suggested the HO229's design allowed relatively easy scaling. A 50 larger version would create a strategic bomber with intercontinental range and jet speed. Basically, a 1940s B-2 spirit. The symposium ended without consensus, but with something more important. Renewed investigation. Teams left determined to find new evidence validating or refuting AI findings. Within weeks, news leaked. What had the AI found? Archives unlocked, secrets confirmed. In the months following the symposium, the AI reconstruction began changing how historians understood not just the HO229, but the entire trajectory of aviation technology during and after World War II. First came archival discoveries motivated by AI predictions. Researchers found overlooked supporting evidence. Mathematical notes in Reimar Horten's personal papers, previously dismissed as unrelated calculations, turned out to be radar cross-section estimates performed in 1944. A production memo from Gottheimer Wagon Fabric mentioned special adhesive formulations matching AI predictions. Each confirming piece made the AI reconstruction more credible. One researcher who'd spent 40 years studying German wartime aviation summarized, "The AI didn't tell us what we wanted to hear. It told us what evidence actually shows once you process it all simultaneously. Something human researchers simply cannot do with this volume of contradictory data." The reconstruction resolved long-standing technical debates. For years, engineers argued about the HO29's center of gravity position. The AI's reconstruction, validated through multiple independent methods, settled the question definitively. But perhaps the most significant impact came in understanding technological progression itself. Traditional history viewed the HO229 as an isolated experiment. The AI reconstruction challenged this narrative by showing how mature the design actually was. It suggested the HO229 represented the leading edge of a technological wave World War II's end had truncated. Consider the B-2 Spirit stealth bomber first flew in 1989, 44 years after the HO229. Both are flying wings. Both use radar-absorbing materials. But AI reconstruction revealed specific design principles in the HO229 that appeared were refined and evolved in the B-2. The AI reconstruction has sparked questions about artificial intelligence's role in historical research. If machine learning can complete fragmentary aircraft blueprints, what else can it reconstruct? The potential is enormous, but so are the risks. What's clear is that AI finally reconstructs. Lost WW2 Horten blueprints represents more than just a technical achievement. It's a new methodology for understanding the past. By processing vast fragmentary evidence simultaneously, AI sees patterns that human researchers miss. But we still haven't answered the biggest question. What exactly left experts speechless? The results left experts speechless. The moment came 3 weeks after the symposium. The research team received access to newly declassified documents from the U.S. National Archives. Intelligence reports from 1945 sealed for 80 years. The documents contained interrogation transcripts of Reimar and Walter Horten after capture, along with technical assessments by American engineers who examined the HO-229 V3 immediately after seizure. What those documents revealed stopped the entire research team. American engineers in 1945 had found something in the V3 classified and subsequently lost in bureaucratic archives. A structural cavity in the wing center section contained fragments of electronic equipment completely burned out but present. The 1945 intelligence report speculated that this might be radio or navigation systems. They catalogued it, photographed it, then apparently forgot about it as higher priorities consumed attention in the war's chaotic final weeks. The quantum AI had predicted this cavity's existence. More than that, based on analysis of the V3's electrical system layout and power distribution requirements, it suggested the cavity was designed to house something specific, an advanced radar warning receiver operating on heterodyne principles. Not just any radar detector, but one operating on principles not publicly developed until the 1950s. The AI reverse-engineered its existence from subtle wiring details, power requirements that exceeded what navigation equipment needed, and shielding patterns that only made sense for sensitive radio frequency equipment. When the team compared 1945 photographs of burned equipment fragments with AI predictions, the match was undeniable. Component mount spacing, cable routing, power connections, even the fragment size and placement, everything aligned. The Horten brothers had attempted to install what amounted to an early electronic warfare system in their stealth aircraft. The concept was complete. Detect the radar, evade before detection is confirmed, and attack from blind angles. It was an integrated stealth philosophy, not just passive radar absorption. But that wasn't what left experts speechless. The truly shocking discovery came when the AI completed the production variant blueprint analysis. The V4 through V7 models were never built. The reconstruction revealed design evolution, suggesting the Horten brothers weren't thinking about 1945. They were designing for 1950, 1960, maybe beyond. The V7 variant included provisions for afterburning engines that didn't exist yet. Wing structures with reinforcement patterns anticipating supersonic flutter loads and cockpit layouts suggesting pressurization systems and life support for sustained high-altitude operations above 45,000 feet. The AI found the design logic embedded in V3's existing structures, reinforcement patterns making no sense for V3's actual capabilities but perfectly positioned for advanced variants, attachment hardpoints for uninstalled systems. Weight distribution that seemed suboptimal until you realized it was optimized for configurations 2 or 3 generations ahead. The Horten brothers had hidden their long-term vision inside the prototype itself, like seeds waiting for the right conditions to grow. One respected aerospace engineer examined the analysis for 3 days before admitting they were building a platform, not just an aircraft, but a technology framework that could evolve for decades. This is how we design military aircraft today. Thinking 3 or 4 generations ahead, building expansion capability into Generation 1. The Horten brothers did this in 1944 with slide rules and intuition. The quantum AI reconstruction revealed something else nobody suspected. The HO-229's design contained embedded solutions to problems the aviation industry wouldn't encounter for years. How do you prevent jet engine compressor stall in a flying wing with deeply buried intakes? The answer was built into the intake geometry, specific diffusion angles, and boundary layer control that wouldn't be formally understood until the 1960s. How do you maintain control authority at transonic speeds when shock waves form and shift? The wing profile and control surface placement addressed it. The AI tested each solution in a virtual simulation across thousands of flight conditions. They worked every time. But here's what truly left experts speechless. The AI's final analysis suggested that with late 1940s technology, full development funding, and 5 more years of evolution, the HO-229 lineage could have produced an aircraft matching 1960s fighter performance in speed, altitude, range, and stealth. Not a prototype or an experimental proof of concept, but an operational military aircraft performing 20 years ahead of its era. The most chilling implication emerged from combat effectiveness modeling. Using complete reconstructed specifications, the system simulated what would have happened if even a modest force of operational HO-29s had engaged Allied bomber formations. In early 1945, the AI ran 10,000 combat scenarios with varying conditions, tactics, and force compositions. Results varied widely, but one pattern remained disturbingly consistent. Conventional Allied defenses would have struggled significantly. The aircraft was too fast to intercept reliably with piston-engine fighters, too stealthy to track consistently with 1945 radar systems, and capable enough to strike and disengage before effective countermeasures could be organized. Then came the final revelation, making international news. A researcher at the German Federal Archives, following AI-generated leads about production authorization patterns, discovered a sealed file from April 1945, a memo from Albert Schaar, Hitler's armaments minister, discussing emergency production priorities in the war's final days. Buried in technical details was a single line. The Horten project is green-lit for immediate mass production. Initial order 200 units 200 HO 229s. The order was dated April 10, 1945, exactly 3 weeks before Germany's surrender. It was never fulfilled. Factories were overrun before production began. But the authorization existed. Germany's leadership, even in absolute defeat's chaos, considered the Ho 229 important enough to warrant one of their last major production decisions. Symposium attendees who first saw the complete reconstruction sat in stunned silence for nearly a minute after the final presentation. Not because they were impressed by technology, not because they admired engineering, but because they realized they were looking at a ghost, a phantom of a history that almost was the quantum A. I hadn't just reconstructed blueprints. It reconstructed a possibility. And that possibility was unsettling in its sophistication, its completeness and its nearness to reality. When the results left experts speechless, it wasn't amazement. It was the profound, unsettling realization that humanity came much closer to a very different 1945 than we ever knew. AI finally reconstructed the lost World War II Horten blueprints. And in doing so, it reconstructed our understanding of World War II's final chapter. The technology thought impossible for 1944 turns out to have been entirely possible and nearly operational. The HO 229 reconstruction demonstrates quantum artificial intelligence's power to recover lost knowledge, but it also shows how close historical outcomes can be to completely different realities. The aircraft that could have changed everything was stopped not by technical impossibility, but by time running out. Today, the AI reconstructed blueprints exist as a complete digital archive. They are being studied by aerospace engineers, analyzed by historians, and debated by ethicists. Some argue we should build a complete flying reproduction to validate the AI's work. Others say that would give new life to technology from a regime responsible for immense suffering. But perhaps the real lesson isn't about the HO 29 at all. It's about what quantum artificial intelligence can reveal when we point it at history's gaps. How many other lost designs wait to be reconstructed?